Okay, so we're going to almost finish up chapter, whatever it is, 17, 18, on radicals, some of which is kind of review, but there's a couple things. So we'll get as far as we can, and then I've already released Monday's folder, so we're going to talk about allylic systems and double bonds. So that video is already up if you want to watch it in the sections of the textbook. So where were we at the other day? Here's where we were at. So we were taking and doing a free radical halogenation of bromine with light at room temperature, and we did pentane. We reacted propane. And we said that there were two distinct products, product A and B. Product A comes from any of the CH3s being substituted, so there were 6 hydrogens that would give us product A, and then B being the CH2, 2 hydrogens if replaced with a bromine would give us product B. So we could make one argument that the major product of this reaction might be A because there's more hydrogens that can be substituted for. On the other hand, product A comes from a primary radical, and product B comes from a secondary radical. And so you could also make the argument that product B will be the major product because it's coming from a more stable intermediate. We're at the point where the question is, so which one of these two is going to be the major product? And we have 2 opposing arguments. The reality is it's going to be a combination of both of these. So that's what we're going to talk about. Okay, so which one is going to be the major product? It's going to depend. What's it going to depend on? It's going to depend on whether we use bromine or chlorine. It's also going to depend on whether we use light at room temperature or we go to greater than 300 degrees Celsius. So those are going to be our factors, and changing any one of those conditions can cause the major product to change. And we're going to be a little more quantitative in terms of being able to determine what the major product is by actually assigning some numbers. But the numbers are just going to be numbers that we assign. And the biggest number is the major product. So let's go through all of this. First, what people decided to do was to try and determine for these reactions how much faster you could form a secondary radical versus a primary radical. Now, the problem is determining absolute rates is nearly impossible. I mean, it can be done, but what we'd instead like to do is we'd like to do relative rates. So if I did this reaction, I could determine by the percentage of the major product, or the percentage of the products, how quickly one radical is formed over another if I do one thing, and that is to factor out the number of hydrogens that are for each product. So what people said was, if I take the percentage of product A and I divide through by the number of hydrogens that give me product A, I will get what I will call a selectivity for A. And in this case, it's the selectivity of forming the primary radical. Okay. Sort of the rate of forming that primary radical. And if I take the percentage of product B and I divide through by the number of hydrogens of product B, that will give me the selectivity of the secondary radical, which is what gives me product B. Again, I can't determine the absolute rates But what I could do is I could say, okay, how about I divide through and say that the relative rate of the secondary to primary would be then saying, okay, well, that's going to be percentage of product B divided by number of hydrogens of B over the percentage of product A divided by the number of hydrogens of A. So in dividing through by the number of hydrogens, I'm basically normalizing the system. I'm taking out statistics. And by taking this ratio, then, I could determine how much faster a secondary radical forms versus a primary radical. And so this is what people did. They took a whole bunch of molecules. They did free radical halogenations. They only looked at the mono-substituted products. And then they took the ratios and kind of averaged them all out. And so here's what we find. We find that for bromination at room temperature, the relative rate of forming a tertiary radical to a secondary radical to a primary radical. So everything is based on the primary radical, is 1700 to 80 to 1. So what does that mean? That means that you form, in bromination, you form a tertiary radical 1700 times faster than a primary radical, and a secondary radical 80 times faster than a primary radical. Okay, using reactions, percentages, and these formulas. And these will vary by book, but usually not too much. And I'll give you these numbers on any quizzes, exams that you'll have. Okay. Now for chlorination at room temperature, the tertiary to secondary to primary ratio is 5 to 3.4 to 1. So that's a bigger difference, or a big difference from bromination. So you form a tertiary radical in chlorination only 5 times faster, and a secondary only 3.4. Okay. So these are what are called our selectivities. And so those numbers are determined by just averaging out a whole bunch of reactions. Going back to the equation that has now the selectivities, that means that if I give you a reaction, and we're going to go back and do this propane reaction, that the percentage of product A equals the number of hydrogens of product A times the selectivity. Being 1781, 5, 3.4. And it's the selectivity of that position, of forming the radical at that position, gives you that product. Okay. So we can use this formula then to calculate a number for any product. The product with the highest number is the major product. If two products have the same number, then they are the major product. So this is how we're going to calculate it. So number one, we should note that there's different selectivities whether you use bromine or chlorine. Where is a bromine likely to substitute in bromination? Which hydrogen is it likely to substitute for bromination? Tertiary, because it's 1700 times, the tertiary radical forms 1700 times faster. And I guess we should go back and say, all right, well, what's the rate determining step of the 6 steps that we wrote on Wednesday? And the rate determining step is when you take your atom, react it with your alkane, and make HBr and that radical. This is the rate determining step for free radical halogenation. So it's the formation of the radical that's the rate determining step. So what we're going to do is we could calculate basically the numbers for each reaction, and then if we want, we can determine an idealized percentage given that set of conditions. Right now we're only dealing with room temperature and using light as the initiator. And I should probably say that if you ever see the H nu term, H nu is a photon of light. So sometimes you'll see light abbreviated as H nu. So let's go back to the propane reaction. Let's use the numbers and predict what would be the major product for bromination and for chlorination. So I'm going to go back here, and I'm just going to basically abbreviate this by saying X2 under the conditions of light and room temperature. I know my first product is the 1 chloro or bromo, and my second product is the 2 chloro or bromo. So for bromination, the percentage of A, product B, over here, the A proton or the A hydrogens give me product A, and the B hydrogens give me product B. So what I'm going to use for the number of hydrogens is the reactant on the left. So for the percentage of A, what am I going to have? I'll just come over here. Percentage of A is going to equal 6 hydrogens times what type of radical gives me product A. Primary, so its selectivity is 1. It's always 1. Because everything's related to that. So it's 6 times 1, which is 6. For B, how many hydrogens? And what's its radical? It's coming from what kind of radical? Secondary, and so its selectivity for bromination is 80. So that's 160. It's as simple as that. I mean, I can't make the math any easier. Will you need a calculator on the test? I hope not. I hope you can do some basic math in your head. All right, so which one's the major product? B. What's the percentage of B? Well, if I asked you to calculate the percentage of B, the percentage of B would equal 1 over 6, or 160 over 166. Right, it's just like GCs in lab. And that's greater than 90%. That one you might need a calculator for. Okay. So, actually I would say what? It's going to be greater than 95%. It's going to be in the 95-96% range. Let's do it for chlorination. So for chlorination, our percentage of A is going to be same formula, 6 hydrogens times that coming from a primary radical, which is 1, is still 6. But now for B, what is it? There's 2 hydrogens, and now a secondary radical has a selectivity in chlorination of 3.4. So it's going to be 6.8 for that one. So what's the major product? B, just barely. So B is just over 50% of the major product. So numerically, this is how we do it. That's how we determine the major product. So everybody kind of with me there? Because we could just stop here and go, oh, I just do these calculations, and then you're doing them, and then somebody says, well, what are you doing? I don't know, I'm just doing what he told me. So let's go into the details. So in terms of which reaction is more selective, the bromination is more selective because you have a greater percentage of one product over another. The chlorination is less selective. And what drives those two reactions is the formation of the radical. When you do bromination at 1700 to 80 to 1, if you have a tertiary hydrogen, that's where the bromine's going. Because to break even, you would need 80 secondary hydrogens, is the way you can think about it. And if you only had secondary hydrogens, the major product would depend on which secondary hydrogen you have the most of, because they're all at 80. But it would clearly go to a secondary hydrogen. So we don't even need to do the numbers if we're doing bromination. If there's a tertiary position, that's where the bromine's going. If there are two unequal tertiary positions, it's going to both. For chlorination, though, that 5 to 3.4 to 1, it only takes like 3 or 4 primary hydrogens to outweigh a 3.4 to 1 selectivity. So in chlorination, the statistics plays a much larger role because the reaction isn't as selective. It's only 5 times faster or 3.4 times faster to form a tertiary or a secondary radical. So that reaction is less selective. So chlorination is going to give you a wider variety of products, at least in terms of percentage. So when we want to put a halogen at a very specific position, and that position is tertiary, we're going to use bromine. If we want to kind of reverse that, we might want to use chlorine. But notice that there's no way for me to stop getting both products. I'm always going to get both products. So, why is bromination different than chlorination? If we go back to that rate determining step of taking your halogen atom, it abstracts the hydrogen from the carbon, it forms the HX bond, and then your carbon radical. The one thing that it's not due to is the formation of a tertiary or secondary radical. These things are the same in both reactions. So the reason that I'm getting bromine more selective is because the bromine, not because of the radical. Which does lead you to, well, if they're both reactions are forming a tertiary radical, it's the same radical. So why is one faster than the other? And that has to do with looking at this overall reaction. So here's what we know, and this is like the first part of the chapter where they go through all the bond association energies. If I calculated the bond association energies for this rate determining step, what I would find is that for chlorination, the reaction is exothermic. And for bromination, because this is the way it works in organic chemistry, it's endothermic, right? It's always one. If we have one, then we have the opposite for the other. So chlorination step is exothermic, bromination step is endothermic. And that's actually what's going to tell us the difference. Now, if I was forming the same secondary radical, I haven't drawn these diagrams exactly the way they should, because what should happen is this energy level and this energy level should be exactly the same. So it's the reaction, whether it's endo or exothermic, that's going to tell us, or that's going to explain to us why bromination's more selective, meaning a bigger difference in percentages of tertiary, secondary, and primary than is chlorination. It's because of the endo or exothermicity of the reaction.
What did you say? Two values would be the same?
These two energies would be the same. This would be the same as this one if I truly drew out the diagram correctly. That's how it would look. Which means I'm starting at different energies, but in the end I'm ending at the same radical. So this sort of this is the beginning of telling the difference. Okay. So everybody with me so far? All right. Now let's drill down on this a little bit more. Let's take my exothermic reaction and say I'm going to form a primary radical, and then I'm going to form a secondary radical. And over here, I'm going to form a primary radical, and then I'm going to form the secondary radical. So this is chlorination, and this is the bromination, and this is the rate determining steps. Why do you form a secondary radical faster? Well, why do you form a secondary radical faster in each case? Kevin?
Smaller activation energy?
Because forming the secondary radical has a smaller activation energy, true. And that reasoning comes from the Hammonds Postulate. Right? The Hammonds Postulate would say that when I lower the energy of the intermediate or of the product, I'm going to get a smaller activation energy. So that's for both cases. And if I drew a tertiary, it would form a tertiary faster. Okay, so we're back to, let's see. For almost everybody, we're back to first semester. Talking about Hammonds Postulate. So let's see. Let me just remind you that Hammonds Postulate, if I have a piece of paper, reaction coordinate diagram. When the reactants and the products have the same energy, the transition state's right in the middle. If I now make it an endothermic reaction, what happened to the position of the transition state? It's closer to the products. If I make an exothermic reaction, the transition state's closer to the reactants. And because of that position, if your transition state's closer to the reactants, that means you have to make very few bond movements or atom movements. It takes less energy, can occur faster. If you got to make a ton to get to almost the product, it's going to take a lot longer and require more energy. So we interpret that then in terms of the activation energy. Okay, that's step number one to understanding this. The real question is what happens in the difference between exo and endo. Okay. And what we're talking about here is we're talking about relative rates. So rate is not in the Hammonds Postulate. Right? Rate is in the Arrhenius equation. So we feed those differences in activation energy along with the temperature into the Arrhenius equation, and we could calculate the rates of forming the primary and the rate of forming the secondary, and we could get the relative rate difference. So here's what happens. If you think about a chlorination reaction, I have two relatively small activation energies that the reaction's looking for. So we take this into the bird hiker analogy. The hiker's looking to go over two small hills. The hiker will always go over the smaller hill faster, but they're two small hills. And the hiker has a lot of energy, even at room temperature. So the relative rates at which they go over those two small hills are going to be closer together. In the bromination, the hiker still has a lot of energy to get over the mountain, but now it's a mountain, not a hill. And it's two mountains with maybe substantially different differences. And maybe not, maybe the same exact difference. But as the hiker is going to go over each of those two mountains, there's going to be a bigger difference in the relative rates of those. We can increase the difference between the relative rates by starving the hiker of energy. Basically starving the molecules of energy, which means we do what to the temperature? We lower it. So when you lower the temperature, you lower the kinetic energy of the molecules. Now you have to be careful, because at some point you're going to have a low energy which is going to maximize the rate difference, but you still want the reaction to go. So if you go too low in temperature, you're going to get no reaction. So as we lower the reaction could become more selective. So the difference here is because the exothermic reaction has a much larger activation energy, the difference between the two is going to be bigger. The relative rate difference is going to be bigger. And if you're doing chlorination with small energies, they're going to be the relative rate's going to be much smaller. And it all has to do with this mathematics. I mean, what I'm giving you is kind of a non-mathematical description. Okay? So, bromination, the difference in forming primary and secondary, it's going to be much different relative rate. Does that make sense? So I lower the temperature. As long as the reaction goes, I can accentuate the rate difference even more. Now, what happens at higher temperatures? The reaction goes faster. Actually, in these cases, all the reactions go faster. So what happens to the relative rates between those reactions? If you go to higher temperature, the rate difference is going to get smaller. And again, that's all built into the mathematics of this equation. We could take it to, that's where the supersonic bird thing comes from. If you now have birds with lots of energy, they can fly over the mountain at nearly the same rate. They'll still go over the smaller mountain faster. So the rates will never become one, but we're going to treat them as if they do. So at higher temperatures, and typically what we say is at temperatures greater than 300 degrees Celsius, because I think somebody actually worked out all these equations and figured out at 300 degrees Celsius, your rate of forming a secondary or tertiary to secondary to primary radicals is going to become 1 to 1 to 1. So in other words, they're going to form each of the radicals nearly identical. So now selectivity isn't an issue. Going back to my equation, the percentage of product A equals the number of hydrogens times the selectivity if the selectivity is always 1, what's the percentage of the different products going to be dependent on? It's totally dependent on the statistics, the number of hydrogens. So, in our theme of organic chemistry, where we're trying to do one thing or the other and have the ability to do both by selecting the conditions, if we go to a higher temperature, it doesn't matter whether we use chlorine or bromine, I'm going to basically get a statistical mixture. Going back to the propane reaction, that means at greater than 300 degrees Celsius, we would have 6 times 1, 2 times 1, and so we would have a 3-to-1 ratio of products. 3-to-1 ratio of products A, which would be 75% A and 25% B. And that's the best I can do for A. I can't get it any higher than 75%. If I want B, I can get it to 95%. But if I want A, if I want the primary radical, that's the best I can do, 75-25. So this gives us the ability to choose the major product if we want to by changing the reaction conditions and by changing whether I use bromine or chlorine. The disadvantage to chlorine is you're going to get a greater percentage of all the different products. And you might say, well, who cares? Well, let's just say you have a company and you're making 1 bromopropane for somebody, or they come in and say, hey, can you make me some 1 bromopropane? And you say, well, let's see, I'm going to do that by free radical halogenation, and the best yield I can get is 75-25 if I do it at greater than 300 degrees. So you do that, you still have 25% of the unwanted product that you have to separate and that you have to find somebody else to buy. Right? Because throwing it away is going to cost you money. So you got to figure somebody else has to buy it. It'd be better if they came in and said, hey, I want B. I want the 2 bromopropane, because we know we can make it in 95% yield, and then we'd only have 4% waste, which we'd have to find to sell to somebody else, because the 4% waste would probably bankrupt us after a while. We couldn't claim that we were green. So free radical reactions, it's very difficult to get them to go to 100-to-1. You can't really get 100%. So that's how we can change the conditions, and that's why they have different selectivities, because the difference between endothermic and exothermic. Does that make sense to everybody? Now you might say, well, okay, this is chlorine and bromine. What about iodine? Iodine is too unreactive, so we don't use it. Fluorine. Fluorine would be here. F2 at room temperature would be 1-to-1-to-1. And the reason is because fluorine is so exothermic that at room temperature you're basically forming all the radicals at the same rate. And fluorine comes in contact with a hydrocarbon, it just explodes. The reaction can't be controlled. And that's just simply because fluorine is the most reactive, one of the more reactive substances that we have. Okay. The only thing that fluorine will not react with is if you take a hydrocarbon and you replace all the hydrogens with fluorines. And that is Teflon. So if you make a long-chained hydrocarbon like a polymer, replace all the hydrogens with fluorines, you get Teflon. And so Teflon we know is like non-stick. I don't think it's gone out of vogue in cookware because the POFA compounds are, I don't know, they just say don't use them because they're allegedly something toxic. But we still have Teflon around. And the reason we have Teflon is because of the Manhattan Project, the nuclear weapons. Because and I'll just side story. When in the Manhattan Project, they had to take the uranium and separate it into different isotopes and enrich it in the one that was going to be used for the bombs. And so they took uranium and they made uranium hexafluoride out of it as a gas. And then they used, diffusion or effusion through pores in order to separate the isotopes based on their kinetic energies and their speeds. So that's effusion through a separator. It's the same thing that everybody's doing to make nuclear weapons. And those are the centrifuges. So when you hear about, this country is not supposed to have centrifuges, and they do, because they're making nuclear weapons. That's what they're doing, is they're enriching their uranium. But the problem was, when they started the Manhattan Project, was fluorine reacts with everything. And so if you're going to make one of these chambers out of steel, the fluorine's going to destroy it. So they had to come up with something that they could coat the insides of the steel containers with that would not react with fluorine, and they made Teflon. And then Teflon was used for anything that's non-stick now. So that's where the Teflon came from. If we try and do free radical halogenation here, if we got the products, it would be a 1-to-1-to-1 selectivity because it's so reactive. So that's how we do the different, that's how we can calculate the percentage, which one's the major product as well as the percentages. And that's what I'm going to ask you to do for a take-home quiz for Monday. And I have it already typed, or I have already written up here. So I'm going to ask you to take pentane and react it with chlorine, bromine, and greater than 300 degrees Celsius. And then you've got to figure out the three products, the three unique products, and then the percentages of each, and show your work. There's three products. Those are three unique products. Then I've got a whole homework assignment, or a whole practice problem assignment to do all of these different free radical halogenations that I've got to get out of the first semester canvas and over into the second semester canvas. I'm not exactly sure how that works, but I will get it done. Okay. So that's what I'm going to ask you to do for the take-home quiz problem for Monday. Okay. Okay, so that's free radical halogenation. And again, big picture stuff, I can't do anything with alkanes but burn them, which is good, but not from a synthetic standpoint. So whenever somebody hands you an alkane and says make something out of it, your first step is always to free radically halogenate it, because once I put the halogen in place, I can make a double bond, I can replace it, I could add carbonyls, I can oxidize the alcohols. I can do all of my steps from that alkane. But the first step is free radically halogenating it. Now, there are a couple other topics in chapter 18. There is the bromination of an alkene, like adding HBr with peroxides. And it goes through the mechanism that we did last semester for anti-Markovnikov addition. I don't plan on going back over that. But there is some new stuff that kind of takes us into Monday. And that is that if I'm going to, let's say do this reaction, and I'm going to modify this reaction on Monday because the product we're going to get isn't the correct product, but we'll play along with me. So we take bromine and light and we react it with this alkene. This hydrogen and this carbon are at a special position. They are called anybody remember?
The allyl.
This is the allylic position. So that's the allylic hydrogen and the allylic carbon. They're next to the double bond. And why are they important? Because I can make that radical, and that radical is actually pretty stable. Well, it's more stable than a normal primary radical.
Can double bond be rotated side to side like with the carbon cation?
Yes, I don't like that. I don't like those terms. I don't like the rotated term.
Or transition.
I like the word resonance.
Right.
That's what I like. It's not just a preference, it's exactly what's going on. So yes, you may or may not have talked about an allylic carbocation in mass spectrometry in lab and how it's stable. So that's the analogy that Josh is making. But this has resonance structures. Now it's going to be, we have to move electrons one at a time to make the resonance structure, so it's a little bit different. But let's say that I split this double bond in half and I give each of the two carbons one electron. So I'm again using half arrows. And then I take this and pair it up with the carbon in the middle that basically had an unpaired electron. So if I do that, I can write the second resonance structure for this primary radical, which is that. And remember, in resonance structures, we're not allowed to move anything except electrons. So that's all I moved here. Okay. I didn't rotate anything. I just moved electrons. So there's my two electrons. So an allylic radical is pretty stable because it has resonance structures. And this allylic radical, it'd be better if it was secondary, it'd be even better if it was tertiary. But being primary allylic is not that bad. And it is better than being just primary. So that's one of the topics that they talk about in chapter 18. Meaning that if I was to do this reaction, I would make, if I was to do that reaction of brominating the allyl, I would brominate at the allyl position. That would be the primary position where bromine would react, just like the tertiary position because of the selectivity. I don't know what the number is, but the bromine will go there as the major product. Although I'll come back on Monday and I'll actually tell you that's not what you're going to get. But it's a small problem. So then we can expand this and we can say, Now this one, I can do bromine and light at room temperature. And the stable radical that's going to be formed is that one. And that looks like an allylic radical, like if I take my piece of paper and I cover up the benzene ring. Oh wait, it doesn't cover it up on the screen, does it? I knew that. Maybe. So if I cover it up, it would be allylic. This one's not allylic, it's called benzylic. So this is a benzylic radical. And so when you have an alkyl group attached to a benzene ring, your preference is going to be, your major product is going to be to brominate the benzylic carbon. It doesn't matter how long the chain is. Okay. Because there's three more resonance structures that you can draw for that radical. They almost made that a homework problem or take-home quiz problem as well, but we'll deal with that when we do the carbocations. Okay, so that's another special position. So when you're doing bromination, your special positions where you're going to brominate to form the major product are going to be tertiaries, allylics, and benzylics. Those are going to be the three top positions for forming those stabilized radicals. Tertiary because it's tertiary, and allylic and benzylic because they can be stabilized by resonance structures. So that is, I think there's one or two more small things that we have to deal with.
Are benzylic and allylic more preferred than tertiaries because of the resonance?
I don't know the answer to that question. The only reason I don't know the answer to that question is because we're being annoyed by this problem right now in actual research. I'm a little surprised, just so you know, sometimes I will look at this and go, did I really teach that right? Alkene, adding HCl to an alkene on paper, we talk about this being really easy. It's not. When you look at the papers, it literally you can stir it for a week and it won't go to 100% reaction. And some Japanese people came up with a reaction. Some Japanese researchers came up with a way to do it in 3 hours, which works. But our problem here is that the reasoning that I just showed you, or I just talked about, the question here is if I add the H+, which of these two carbocations is the most stable? The benzylic carbocation or the tertiary carbocation? And so we've been having difficulties with this because it's actually, when we add HCl to this, the H goes here and the Cl goes there, 100%. And that kind of violates what I've been teaching for the last few years, which is, it's a secondary benzylic. That's got to outweigh a tertiary. Yeah, no, it doesn't. It's not. So we're kind of we're a little stunned by that. Then the NMR broke, so we got good spectra before that because it's easy to figure that out. But this is Brian's research project, so. And there's a reason for this that I think that it kind of makes sense, we think. So I am not going to go out on the limb anymore and try and rank these things, the stabilities of these, because if and when I give a talk to this in peers, the first question I'm going to poll the audience is, so which one of these two is more stable? And then there'll be debate and argument and everything will ensue, and I won't even get a chance to talk. But sometimes it's not as easy as you think, and sometimes it's not as simple as you think. So is benzylic more stable than tertiary? I don't know. We'd have to I'm afraid we'll end up with the same problem here. So this is real life. Okay. All right. So anyway, when the NMR comes back up, we'll be able to figure that out. Okay, here's your home.